Let's do this one. This is something that you certainly know about because you know how to represent numbers inside a computer. Okay, so if you have a bit representation of a number, something like that, you know that to be like, I don't know, 2 to the 0th, this is 2 to the 1st. Well, here I have 2 to the second, this is 2 to the 3rd, so you add those up. Okay, and it works out to 1, 2, and 8. That's 11. So that number n is represented as 2 to the 3rd plus 2 to the 1st plus 2 to the 0th. That's 11. Okay, and so on. So you know how to represent each number. You know that every number can be represented as a sum of powers of 2. That's nothing new here. Okay, so this is something you've known for a long time and haven't questioned. Today we're going to prove that. So now we're going to use induction to prove this fact, that any integer is the sum of powers of 2. So here's a proof. So you'll be helping me with this proof, right? So this is a straightforward application of induction. So proof. Oh, well, maybe it's not so straightforward because at some point we'll have to just think clearly how to apply it. But the template itself is here. Okay, so we know what to do. Everybody knows. Template, same thing. Okay, so looking at the cheat sheet that you brought to the quiz, okay, I have to say that the proof is by induction. That's the first thing I say. The proof is by induction. Okay. What should I say next? What should I do? What's the next thing to do?
Restate P of n.
Exactly. Let the proposition. Let P of n be every n is a sum of distinct powers of 2. Okay. In gray, I'm going to have it, I'll express it, same thing. Don't have to write this down, but a little bit more concretely. So here's an example of an n. So P of n could have written down this way. Some powers of 2, like power 1, power 2, some powers. Maybe I have like L of them, I don't know, where these P1, P2, these powers are all distinct. Okay, so that's our proposition. That's what we want to prove, that this holds for every n. So want to show this holds, want to show Pn holds for every n. And here Pn itself, okay, just to be clear, it's P of n is n is a power of 2, with distinct powers of 2, like this, and P of n. Okay, so whatever's on the screen, so you see it. Okay. What do I do next? So I want to show that Pn is true for every n. What do I check next?
The base case of P of 1.
Okay, so is P of 1 true? That's exactly right. Is it true?
Yep, yeah, just 2 to the 0.
Yeah, because 1 is a sum of powers of 2. Which powers of 2? This power of 2. There's one term in the sum. It's 2 to the 0th. So that checks out. Inductive step. What's in the inductive step? Okay, so what's in the inductive step? Is that what's in the inductive step? Okay, well, how do I show that? How do I show that P of k plus 1 is true? How do I show that? If k plus 1, but it can be made. So let's do it. Yeah, okay. If k plus 1 is odd, so okay, then help me argue this. If k plus 1 is odd, by the inductive hypothesis, if k plus 1 is odd, k is the sum of powers of 2. It's even, but it's also a sum of powers of 2, right? By the inductive hypothesis. Do people agree? What does P of k says? Well, the inductive hypothesis says that k and also everything that's before k can be represented as the sum of powers of 2. So let's say this is the representation of k. Now, because k is even, okay, these powers, P1, first of all, P1, P2, and PL, these are distinct powers. And none of these P's, powers, is 0. I do not have, so here, we do not have the 2 to the 0 term. Because 2 to the 0 is 1. And every other positive power of 2 is even. Because k is even, then because k is even. Right? Right? Do people see that these are powers of 2? K is a sum of powers of 2 by the inductive hypothesis, and all these powers must be greater, strictly greater than 0. So k plus 1 is equal to this whole thing is equal to this plus 2 to the 0, which is 1. And because 0 was not present in those powers, okay, here P1, P2, PL, 0 are all distinct, right? Because P's were distinct and 0 was not present among them, I added 2 to the 0th power. I have a representation of k plus 1 as the sum of distinct powers of 2, for sure. And I've proven my implication. Do people agree that this completes the proof for the special case where k plus 1 is odd? If k plus 1 is odd, then we're done. But let's consider the case where, more interesting case, where k plus 1, this was pretty straightforward, right? So if k plus 1 is even, then what do I do?
Can we consider that k, we have k minus 1, and since k minus 1 is within the range that we know is true, piece of 1, piece of 2, or it's a piece of k, if we just add 2
Okay.
To k minus 1, we know that we get to k plus 1.
Well, anyone can suggest that that's a good idea, but anyone can see the flaw in this? First of all, here was a good idea. Here, this one. What's wrong with this? Why is this flawed? Why would this not be accepted as an argument? Anyone? That's because when you say that k minus 1 is represented as a sum of powers of 2, what if some of these powers includes the first power of 2 already? Then when you're adding another first power of 2, you're repeating the power. We want to show that you're representing each number as a sum of distinct powers of 2. So this, while a very good idea, in this case will not hold water as part of the proof. So it wouldn't make it to the proof. Well, somehow we need to use the inductive hypothesis. We know that like the half of k plus 1, because k plus 1 is even, it's half of that integer. Is strictly smaller than k plus 1, and it's an integer. It's not like 7.5 or any a number like that. It's a number. It's an integer. K plus 1 over 2. That's an integer. Is a power of 2. Power of 2. I'm sorry. Sum of powers can be represented as a sum of powers of 2. Powers of 2. Of 2. So by the inductive powers of 2, by the inductive hypothesis. So A is some powers of 2. I don't know, some m of those powers of 2. Okay? Then k plus 1 is, well, it's 2a, right? 2 times, well, 2 times a, which is 2 times this whole thing. All right? Which is k plus 1 equals 2 p plus 1, 2 p2 plus 1, plus blah, 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 2 pm plus 1. Okay, so what do we have here? We have a representation of k plus 1 as the sum of powers of 2. Are those powers distinct now? Why are they distinct if they are? Because by the inductive hypothesis, k itself, not k, I'm sorry, a itself is represented as the sum of this. These are where p1 and p of m are distinct. These are distinct numbers. So p1 plus 1, p2 plus 1, p of m plus 1, these numbers are distinct. So p1 plus 1, p2 plus 1, pm plus 1, these are all, these powers are all distinct. So we've just shown that k plus 1 can be represented as a sum of distinct powers of 2. And we've only used the inductive hypothesis when k plus 1 is even. Does that make sense? Does it make sense to everybody? Again, the template, it's the template, following the template, that's straightforward. Here we did have to do some work. It's not immediately clear. This is not something that can hit you immediately how to do the inductive step. But here's a clear inductive step. Okay, so, and this, I have to say that because I've shown the base case and the inductive step, therefore, by the principle of math induction, Pn, this proposition here, has to be true for every n. So now the proof is complete. Okay, so that was another example of a proof by strong induction. There is another example with the stamps, but how about you guys do it at the recitation if we run out of time? What else did we talk about last time?
Recursion.
Sorry, recursion, yeah. So we talked about recursively defined functions, right? If you remember. So this was an example that we did last time. So you have a function f that's defined recursively. So how do you define a function recursively? You have a definition of the function at some base case, at some basis step, in this case, the definition of the function at 0. And then you have a rule of how to define this function at any number based on the value of this function on the previous values of n. Okay. And that was a recursive definition. We could have defined, for example, n factorial recursively. How do you define n factorial recursively? Real quick.
you multiply n with the previous term.
Yeah. So a sub 0, the term is going to be 1, and the nth term is going to be whatever the previous term was, times n. That's the definition of the nth term. Okay, so for example, a sub 2 is 2 times 1. A sub 3 is 3 times a sub 2 is 3 times 2 times 1, and so on. A sub 4, that's a recursive definition of a factorial. A sub 3 is 4 times 3 times 2 times 1, and so on. You got the idea. Okay, so same thing with the symbol. It's on the other video. Okay, so you get the. Okay, so we can also define sets using this recursive idea. So you can define something like a set of numbers, some subset of the set of numbers recursively. All you need is a basis step. The basis step will tell you what's included in this step, the concrete elements of the step, so-called initial collection that belongs to the step. And then you have a rule. The recursive step is a rule for generating new elements from what's already in the set. So let's give an example of this. Here's an example. I'm defining a new set S. I have no idea what's just as I had no idea what factorial was until I had a recursive definition. Or I had no idea what the value of the function was before I had a recursive definition. Here I have no idea what's in the set that I'm about to build, but I know that my basis step is telling me that 3 is in it. So this element 3 is definitely in it. 3 is in it. But then I also have another rule, in addition to this basis step that gave me the initial element, that if I have 2 elements that are already in the set, then their sum will be in the set. So let's enumerate exactly what's going to be in the set. Everybody sign in. Okay. 3 is in the set. What else is in the set? If I have 2 elements, so 3 is in the set by the basis step. 3 plus 3, 6, must be in the set, right? Because 3 is in the set, 3 is in the set. The sum of anything that's already in the set must be in the set. That's what the rule says. How about 3 plus 6? Whatever that is going to be in the set S. Why? Because 3 is in it and 6 is in it. And if I have 2 elements already in S, then their sum is going to be in S. So a 6 plus 3 is also in S, but I've figured out already that that was 9, so I don't have to rewrite this again. So I'm going to like scratch it out and say that's 9, that's already in the set. I also have like 3 plus 9 now in the set. If I apply this recursively, so something like 12 happens to be in the set. Well, I could also write that 6 plus 6 is in the set, but I figured out that 12 I've already included it in my set, so I scratch it out. So 3 plus 9, either one of those rules. So use the rule, you keep applying the rule. Then you have something like 9 plus 3 is in the set, or 3 plus 9. That's already in there. So something like 6 plus 9, or 9 plus 6 is in the set. So you get the idea. All I'm doing here is generating new elements based on the rules that I already have in place. The base case gave me one initial element, and that from that initial element, then given the rule, I can generate new elements. That's a recursive definition of a set. Now, you can see that it mirrors the structure of inductive proofs, although here now we're not proving anything. This is a definition. We're defining sets recursively. But we can often use induction in proving certain facts about sets that are recursively defined. So let's try this example here, this very example, to see what I mean. First of all, what's in this set S? What's included in it? What kind of elements are in there?
Positive multiples of 3.
Yes. So that's a good hunch. That's our conjecture, that positive multiples of 3 are in it. Now here's a question. Are all positive multiples in it? So for example, 2166 is a multiple of 3. Will I be able to generate that number, that particular number, 2163, or 2,000,001? 2,000,001, that number is a multiple of 3. How would I be able to, would I be able to generate that number using this definition? That's the question. So the question is this: is every multiple of 3 going to be generated by this recursive definition? And also, is there anything outside of it? Is maybe some non-multiples of 3 can be generated by this definition? So, for example, 76 is not a multiple of 3, right? Can a number such as 76 be generated by this definition? So, do you see what the question is? The question is that we have a conjecture that we're generating multiples of 3. We just want to be sure now that nothing other than a multiple of 3 will be generated. And moreover, every multiple of 3 will be generated. Do people see the claim that we're making here? We want to prove this now. So here's the claim. So by the way, you can skip this. We don't have time for this. We'll talk more about homework assignments. You can skip this one when you're reading assignment, like defining the structure. Although it's a good example to go through this now. At the end of the class, we may have section about computation and computability where this will become very important. These are interesting examples that lie at the foundations of computing. But we don't have time for this right now. So let's stick with this recursively defined set here. So again, this is just the same definition as on the previous slide. I'm going to copy this way of defining an S. This is going to be my thing that I will copy in the next slide. Here, this is how we're defining S. I have a basis step and a recursive step, the rule of generating new ones. And here's your conjecture. Here, it says that this set is a set of all positive multiples of 3. That is, I can generate all positive multiples of 3 and nothing outside of it. This is what we need to prove. So help me out. Now you're going to help me prove this. We'll have a nice proof here, and you're going to help me out with that proof. Can somebody help me out? What is it that I want to show? So what am I? So I'm proving this proposition. This is my theorem now. Proof. What do I need to do? So here's just to restate the theorem. Let A be the set of all multiples of 3. Okay, so you can define it this way if you like these set builder notations, whatever you're used to. You can say it in words, or you can, maybe like in part 1 of this class, you were asked to write it down this way, whatever makes you happy. But A is the set of all multiples of 3. Okay, set S is generated by this. We'll make it purple. This is S is defined like this. Our claim is we want to show that S and A are one and the same set, right? Is everyone clear? That A and S are one and the same set. Okay, so if you want to call this purple S, fine. So S is a recursively defined set, just as we did a few minutes ago, and A is just a set of all multiples of 3. We want to show that all the multiples of 3 are generated by S, and everything that's generated by S is a multiple of 3. All of them are generated. Okay, so to show, how do you show the equality of two sets? Okay. To show show the equality of these two sets in 2 steps, which you will help me now that you're okay, well, maybe, okay, but help me anyway. We'll do this in 2 steps. Step 1 would be to show that A is included in S, and now help me parse this. A is included, okay, so step 1. And step 2 will be to show that everything that's generated by S is going to be a multiple of 3. Is it clear what we're doing? We'll take this in 2 steps. Okay, 1. So now we're showing that A, okay, we'll show that A is a subset of S. Okay, let's say it in words. What am I trying to show? So that we don't get lost in a proof. We don't see the forest for the trees. We show that this holds by math induction. So now we're going to use induction to show that every multiple of 3 can be generated by S, by this rule. This generates every multiple of 3. Why? How does it generate every multiple of 3? Okay, so now it's going to be a straightforward inductive proof. So the cheat sheet tells me the first let P of n. Okay, so what we're proving here's 3n. Okay, let Pn. So what should Pn be? Help me out before I write it down. Correct version of it. What am I proving here so that we're not lost? Like how many people are spaced out right now? Please, how many people we have? Let me just make sure that we're present and not just lost. Please turn on your, please don't watch YouTube cartoons, right? Help me out with this proof. Okay.
We're trying to prove that 3n belongs to S for all n
Yeah,
greater than or equal to 1.
Yes, exactly. Belongs to S for all. That's exactly right. That's exactly right. This is what we want. That's our Pn. And now I want to show that Pn holds for every n. Oops. P1 is true because, why is it true? 3 times 1 is in S by the, now I'm going to go purple because our S is purple, because by the basis step of the definition of S. Okay, so P1 has to be true. Everybody agree? This has to be true. Okay, now what's the inductive step? Inductive step. Again, this is going to be very, very straightforward, unlike the thinking we had to do before, but it will be only straightforward if we know what these propositions are, if we clearly have all our PNs, PKs, PK plus ones, if we have all of those guys clear in our mind. So what is the inductive step?
That if P of K is also true, then P of K plus 1. Wait, how do I word this again? Like if P of K is true, then P of K plus 1 is also true.
Okay, so what's P of K plus 1 is true? What is it?
That 3 times K plus 1 belongs to S.
Exactly. That is, right, belongs to S. But it does because 3K plus 1 is 3K plus 3, and this is by the inductive hypothesis. What does the inductive hypothesis say? That P of K is true, right? We're doing simple induction. We get to assume that 3 times K can be generated by S. That's what we get to assume. Does that make sense? So it's important to keep logic clear here, in addition to doing this math. Right? Does that make sense? So the inductive hypothesis says that 3 times K is already generated by this recursive step here somewhere. So if I get to assume that 3 times K is in S, and if I already know by the basis step that 3 is in S, what permits me to conclude that PK plus 1 is true? That is, what allows me to conclude that this is in S because of the recursive step of the definition of S, which is at the top of this page, which says that the sum of 2 elements that are already in S must also be in S. So recursive step of S definition, let's call it. Does that make sense? So now let's argue the converse. The second piece will be easier to show, actually. I mean, will be less work to show. Maybe I'll write more, but it will be less work at the end. So now we want to show that anything that's if it's generated by the recursive definition, now it will be a multiple of 3. Now that's what we need to argue. So that is anything, by anything, well, any element, anything generated by the recursive definition, by this purple, the S definition above here, this one. Maybe we should copy it one more time down here, although people now know what this is, but still just have it there. By the definition here, okay, by the S definition, is a multiple of 3, is like 3 times M, is a multiple of 3. Multiple of 3. Now that's what we need to show. Okay. Now the arguments you've suggested before may come in handy. So first of all, basis step of the S definition, gives 3. And 3 is a multiple of 3. So we're done here. Anything that the base case generates, basis step of the definition generates, it's a multiple of 3 because it's a 3, it's a multiple of 3. Gives 3, and 3 is 3 times 1, multiple of 3. Okay, 3 times 1, multiple of 3. So that's done. Now, the other thing that we need to verify is that anything that's generated by the recursive step is going to be a multiple of 3. So what does the recursive step say? If I already have 2 elements that are in A, that are multiples of 3, then their sum is going to be in S. That's what the recursive definition says. Okay, so if I have, now check recursive, now check recursive step. So what we're checking here is that anything that's generated by the recursive step is going to be a multiple of 3. It's going to be in A. So S, anything that's generated by the recursive step of S is going to be in A. Okay, so what does the recursive step generate? It takes, recursive step takes X and Y. I think this is what you may have had in mind before. Takes X and Y that are already in A, that are multiples of 3, and adds them up and says, this is now in S. And says X plus Y is in S. That's what the recursive step says. It takes 2 multiples of 3, X and Y. So X is like 3 times M. So let's say X is 3 times M, and Y is 3 times L. Okay? And the recursive step tells me that X plus Y is going to be in S, can be generated by S. This means, but X plus Y, now I have to show that that is also in A. That's what I'm after. I want to show that this, whatever's generated by this recursive definition now, is also a multiple of 3. But that's easy to show because, but that's easily seen because X plus Y is a multiple of 3, is 3 times M plus 3 times L. That is 3 times some integer, like M times L. This is 3 times something, okay, is a multiple of 3. Is a multiple of 3. And therefore, is in A also. So what we've shown that anything that's generated by S is in A also. So now we've proven the inclusion this way. Anything that S generates is a multiple of 3. Right? Do you see the logic? So it's important to not get lost in this. That's kind of lengthy argument, seems like, but it's really, okay, so we wanted to show 2 things, just to review. We wanted to show 2 things. Just as before, now just stepping aside for a second so that we don't get confused with it. Now, before we had these definitions like n factorial or 2 to the n, that was our sequence. right? To take a different example, just stepping away from what we just proved in a second. I just want to draw an analogy. So we have on the one hand, we have this definition that we're used to from calculus. That's the easiest thing to see for us as a human. That's why we have this notation for the sequences. 2 to the n, I know that this gives me this sequence. Well, let's say I start at 0, okay? 2 to the 1, 2 to the 2. I know what this sequence is, right? That's one definition of that sequence. Easy for a human being to see. For a computer doing some task that uses this sequence somewhere in some subroutine somewhere, it may be easier to have a recursive definition of the same thing. It may be easier for to say not this definition, but to say that in order for me to know what the nth term is, I want to know what the first term is. That's going to be 1. And then I have a rule for computing any term, the nth term. The nth term is going to be 2 times whatever the previous term was, starting at n equals 1. Okay, so it generates a0 equals 1. Then it generates a1 equals 2 times a0, which is 2 times 1. So that's going to be 2, and so on. a2, which generates 2 times 2. That's going to be 4, and so on. So it generates exactly the same sequence, but as a result of a completely different definition, of a recursive definition. Now, for a human, in some contexts, this may be easier to deal with. Maybe for a computer, for some alien, it may be easier to deal with. We have these 2 different definitions that give exactly the same mathematical object. Same thing is happening here. Coming back to this example. We know what multiples of 3 are. I mean, these are all these guys, 3 times n's, for when n is greater than or equal to 1. So I have this set. It's not a sequence, but set, like 3, 6, 9, 12, 15, 18, 21, and so on. All these multiples of 3. Okay? Now, what we've done is we've defined the exact same set recursively. When we gave this recursive definition, we suspected that we were getting these multiples of 3. So we checked it. We checked, is everything that's generated by this recursive definition a multiple of 3? It turned out yes. Is every multiple of 3 generated by the recursive definition? The answer turned out to be yes. So we concluded that these definitions are equivalent. They give the same mathematical object, that sequence of integers that are divisible by 3, and only those. Does that make sense? Again, these are alternative definitions. In some contexts, for some computer or some, this may be easier, or this may be easier. In another context, it all depends on the applications. But from a mathematical standpoint, these are completely equivalent ones. And this is just purely mathematical phrase. It's people contemplate the equivalence of this for no good practical reason. But there are practical reasons for considering different definitions also. Okay, now everybody knows what a graph is. I'd like to give another structural definition of a tree. So we'll talk about graphs a lot in this class. So a graph is really a collection of objects that we'll call dots or nodes or vertices, whatever, call them bobs if you'd like, or blobs, whatever. So objects, some pairs of which are singled out. And those pairs that are singled out are connected by an edge. And the entire structure, this collection of dots, some pairs of which are connected with edges, the entire structure is called a graph. So example, dots are all the people on Facebook. When 2 people are friends on Facebook, it's a symmetric relation. When 2 people are friends on Facebook, draw a line between them. So you represent each person with a dot, draw a line amongst friends, and you get some kind of structure that looks like this. Call it a Facebook graph. Okay, that's a Facebook graph. Okay, that's just one example of gazillions. Okay, now, so here's another example of a graph. We'll later call this a complete graph on 6 vertices. I have a special notation for it, but that's to come later. Notice that this graph, for example, here has something called a cycle. A cycle is sort of a path. I have to define all these terms, and we will, but you get to start at any vertex, follow an edge, okay, and without lifting your pencil here, I came back to the same node where I started, and we'll call this a closed path, sometimes called a cycle, okay? And we'll get into the terms and definitions and so on. Now, a special kind of graph, okay, also we call a graph connected if you can get from any vertex to any other vertex in the graph. So there is a path that reaches, in this graph, there's this direct path from every vertex to every other, but you can imagine a graph where you have to traverse these vertices, these edges to get to some other vertex. If you can get from any vertex to every other vertex, it's called a connected graph. Okay, so a tree is simply a connected graph. That doesn't have any cycles. That's a tree. Now, there are alternative definitions of trees, and it's a good exercise, again, in logic, not math. Well, I guess call it math exercise too. But really, it's an exercise in logic to prove that all these 6, whatever definitions there are of what a tree is, that they are all equivalent, right? It's a separate exercise. Today, we're going to give one particular definition of what a tree is, and we'll give a recursive definition because that's what we're covering. So now we'll give a recursive definition of what's called a rooted tree. A rooted tree, why rooted? Well, you can designate one special vertex as a root in this tree. Just call it a root. And by the way, so for example, I could call this guy a root. By the way, I didn't have to call this guy a root, although computer scientists would, if you ask a computer scientist where the root of this tree is, they will point to this particular vertex here. But from a mathematical standpoint, it doesn't have to be that. I can call any of these guys a root. Okay, and then if I give that to a computer scientist, the computer scientist will draw it a little differently, but it still will be the same tree, just drawn differently. Anyway, all of these guys, okay, are trees. And if you have some experience with the trees, you may not have drawn the trees like this. You may have drawn them like that. But these are all trees. Okay, anyway, leaving that aside. Now, I want to give a definition of a tree. In fact, I'll start with defining the full binary tree, in fact, right away, without wasting any time because we're running out of time. And then we'll prove some facts about those trees. So let's get started here. I have a definition here somewhere. Here it is. Just as with that set S, the multiples of trees that we've just defined, we're going to have a definition. This definition is going to be a recursive definition, which will tell me in the basis step which particular objects we get to call trees. So this one says that an empty set, something that does an empty set, nothing is a tree, it says. Okay, so I have some way of denoting what nothing is. So this is the usual symbol. So this stands for nothing. So nothing is a tree. Okay, okay, so nothing is a tree, fine. But then I have the rule for generating more elements of this set of trees from nothing. So something comes out of nothing here. Okay, so leaving these jokes aside, so here's a rule for generating something out of nothing. You say that T is a tree, so now I'm generating a new object that I call a T, tree, and I'm doing this as follows. If I have 2 elements that are already in this set that I'm defining, like T1 and T2, and recall that for each one of these trees, T1 and T2, I have one vertex that's specially designated as a root, right, as a root. So these guys have a root. Then to create this T, and I write this T down as T1, T2, calling T1 the left subtree and T2 the right subtree of it. I generate this T as follows. I take a new dot, and I call that dot a root. And I go ahead and connect that new dot with the roots of the other trees. And I say that this new structure now, this T is going to be that new structure that is constructed the way I just outlined. This will be a rule for constructing new trees out of the trees that we already have. So let's see concrete examples. So basis step. So it's clear, right, what this does, like at least in words for now. Now let's see what's going on. So basis step only generates, it's not very informative. Basis step, well, I mean, it's a step that generates nothing. So this symbol represents an empty tree. That's a tree. Now, inductive step, the recursive step. The recursive step, I hope it didn't put, well, I copied this from the book, so it should be correct. So recursive step says this. Take a root, R, and connect it to the roots of the other objects that are already in this set, the other trees. But so far, we just have like empty set inside. The empty set is the only tree that we know about. So if I take a root and connect it to like an empty set, okay, like an empty set like this, empty, T1, empty. Okay, and to the root of T2, and T2 is also empty. Okay, so I really get just this one structure that has, okay, just this is the only thing that we get. Like this is the only thing that we get, root, a dot. So apparently a dot is a tree now, according to this definition that we just gave. Does that make sense? So now we have two elements in this set. An empty set is a tree, and a dot drawn on a page. That's a tree, apparently, according to this definition. Okay, so we continue. Now we're going to generate more trees from what we already have. So we already have two trees in there, empty set and the root. So, okay, so let's take this, again, definition. I'm looking. So this is now my cheat sheet. So I'm looking at the recursive step at my cheat sheet. And the cheat sheet tells me that to generate a new element of this set, it says, take a new dot that you call a root and connect it to the subtrees that you already have, T1 and T2. In place of T1 and T2, you can pick any of the elements that are already known to be in the set. Okay, so take, I don't know, take an empty set on this side. So take this new root and connect it to like an empty set. Well, I should have drawn it gray when I connect it to an empty set. So let me do that. So I take and connect it to an empty set, for example. And to the right, I connect it with another tree, T2. And this other tree, T2, will be one of those roots that I already know to be in my set. Well, that's one way of constructing a new tree. I could have done it differently. I could have taken this new root and connected as a T1 to this, and T2 is empty, like that, T2 tree. Okay, so anything in purple is a tree. So this structure is a tree. I also can take a new root. Left subtree is going to be another root. Right subtree is going to be another root. That apparently is a binary tree, is a rooted binary tree. This is now the new root. And I can continue this process. I can take another recursive step. So another recursive step. Okay, so let's do one more. Take a new root and connect it with everything that I have so far. So for example, this tree is going to be on the left, attached to the left, and this tree attached to the right. Now this is a new tree, and so on. So I can have maybe this tree attached to this side, and then this side another tree, like for example this one, and so on. So you get the idea. This is yet another tree. Okay, so do people get the idea of what's happening here? Now this is like a drawing representation of these objects that are being generated. And the reason we have them is because we are visual beings and we like to draw stuff. If an alien civilization descended that didn't have the same visual capacity and processed this information differently, they're more likely to understand the abstract definition and maybe not draw their things. They may be representing this in sounds, for example, or in some other way that's unimaginable to us. But the abstract definition, the recursive definition, is still the same nevertheless. And it's nice to have this representation because our modern electronic devices, at least as of now, sometimes are better adapted at understanding and processing data in this recursive form. So it's nice to have these recursive definitions of these structures. So knowing that a structure like a tree is recursively defined, just the very fact can be taken advantage of in programming, for example, and compute various properties of the trees based on this recursive definition. You can write a recursive function, for example, or method, depending on what you're doing in software, to say something about to compute something with a tree. Okay, so that's a separate issue. All right, so now we didn't get to complete everything that we wanted to complete. So now we're done with strong induction. So strong induction will be on the test. So in fact, the next test, the next quiz, will have questions on strong induction and induction. I will not yet bring the questions on the trees because there's more that I want to discuss, okay, with regard to chapter 5.3. Therefore, because this current homework includes questions both from chapter 5.3 and from chapter 5.2, I will postpone the entire assignment with the understanding that the piece that pertains to 5.2 strong induction is still due before the quiz. So just to be clear, the quiz will have questions on induction and just some very basic, straightforward definition. You may have a question on a recursive definition, like the function values that we define, like it's something for the very basic. But I will not ask you to do any proof with regard to trees, because I want to do like another proof next time. So to prove some fact about the trees, like binary trees. Okay, so next time we'll just review this, what's called structural induction. Okay, yet another form of induction is what we're discussing now, structural induction. So I will, if you've completed this assignment, great. I mean, you can theoretically, I mean, there's really not that great need to postpone the assignment, but because you have this like wellness day, this pseudo wellness day, it's just one day. Okay, it's questionable how much it contributes to wellness, whatever, but that's what you have. So I decided to postpone this assignment. You could complete it, but you know, let's just have like half a lecture of discussion on another proof related to trees. Let's talk about trees a little bit more, because we have a huge new section coming up on graphs. So this is, you know, this is a discussion to be had anyway. So so I'm postponing the assignment with the understanding that you'll be ready to do questions on strong induction and usual induction, and have some basic understanding of what recursive definitions are by the quiz. Otherwise, we're postponing. Okay, I think I've repeated that several times, so people are tired. You get the idea maybe, right, from the first time, but I said it like 3 times. Okay, any questions?